All right, so we're going to talk about multivariable functions. And now in Calculus 1, we talked about functions of one variable. So functions that look like this. And a lot of times we wanted to think about a variable y being a function of this one independent variable x. So y would depend on the independent variable x. And the functions would take, say, subsets of the real line, say open intervals or closed intervals. And what it would do for every real number in this interval, or for every real number in the domain of f, we would assign a real number. So what we have is that f of x is also a real number. So for every x in this interval, so this is just an example of a function of one variable. We take a number and a subset of the real line, and we assign a real number for each x in the domain of f. So in Calc 3, or multivariable calculus, things get a little bit more complicated, because instead of considering functions whose domains are subsets of the real line, we're going to consider functions that look like this. We're going to have a new variable z that's going to depend on two independent variables, x and y. And so the domain of our functions for functions of two variables are going to be some subset of the xy plane, like this. And now for each point in this region here, we're going to assign a z value. So what we can imagine is that within this domain, the actual graph of the function is filling out space either above or below the x-axis. So you can already see that there's some challenges in visualizing these functions. Now we'll see a couple ways to make it a little bit easier, but this is sort of just highlighting the initial challenge, that the domain of these functions of two independent variables are going to be these regions in the xy plane. And we can even take it a step further and consider functions of three variables, three independent variables. And now what these functions are going to do is they're going to take points in space. And so the domain is going to be regions, three-dimensional volume regions, and we're going to do the same thing. We're going to take a point in that volume region and we're going to assign to it a real number. And now another important thing to note is that even though we have more than one independent variable, we only have one output variable. The output is still going to be just a real number. And so that's why these are sometimes called scalar valued functions of more than one variable. But this is in stark contrast to what we considered in the previous topic, which was vector valued functions, where we were actually assigning vectors as the output of our functions. Here, our outputs are always going to be scalars. So we already talked about how functions of two or even three independent variables are very difficult to visualize. And now there are graphing softwares available to help you visualize these functions. But one way to do it is just to use what's called level curves and level surfaces. So I'm going to illustrate this idea with a function of two variables. So let's say I have this function, and now again my output is going to be a scalar for given two independent inputs, x and y. So this function is going to have a domain. So domain of f is going to be some subset of the plane, because for each pair x and y, I'm going to assign a scalar. Okay, so let's say this region in here is the domain of my function. Okay, so as you can see, I need a third dimension to really be able to plot these z values. So if I have a point here, then I really need to kind of go either in or out of the page in another dimension to be able to plot these values. But one thing we can do to get around that is to plot what's called level curves. And so what is a level curve? Well, a level curve is essentially just a plot of a contour plot, or if you've ever seen a topographical map that shows elevation, that's basically what we're doing here. So what we're going to do is we're going to fix some values of k. So I'm just going to take a constant k, and I'm just going to see, okay, what xy points of my function f equal this value k. And so what that's going to do, so let's say this is k1. What I'm going to see is that this is actually going to trace out a curve inside my domain. So maybe this is f equals k1. And let's say I have k2, a different number. And I set f equal to that number, and I find the xy values that give me an output of the scalar k2. And so maybe it traces out a different curve, like this. Okay, and then I can do it again with some number k3. And this is exactly what you do with a topographical map or an elevation map. You say, okay, here's my map, my two-dimensional map, and what I do is I plot all of the points that have the same altitude. So along these curves, the altitude is the same. And so you can think, okay, well, going up this way, I'm increasing in elevation. And so you can start to visualize what this surface might look like without actually having to kind of have the skills to draw three-dimensional perspective drawings using these level curves. So we saw with functions of two independent variables that we had some chance of actually visualizing the graph of the function, even without using level curves. But using level curves, it's relatively simple. But if we consider a function of three independent variables, well, now my domain is actually a three-dimensional volume, and that's as high as I can visualize, a three-dimensional volume. And so it's going to be impossible to actually, in our mind, visualize the fourth dimension of the scalar that we're actually plotting, given our x, y, z points that's in our domain of our function. So let's say we have some sort of region. I'm going to draw it like a spherical region like this. That's the domain of f. So this will be the domain of f. Is this sphere right here. So any point in the sphere, I can assign a scalar value. And the way I like to think about this, or the example I like to fall back on, is, okay, I live in a three-dimensional world. And here is sort of this region. And now what can I assign to each point in space? Well, my go-to example is temperature. Now, I can see this point in space, W. I can't actually see its temperature, but I can imagine that there's some scalar number associated to this point in space that's its given temperature. Or another thing that people like to do is coloring. So in our three-dimensional world, even though I can only see points in three-dimensional space, I can think about each point being assigned a color. And so somehow that's giving me my scalar output, or giving me a way to visualize my scalar output. So that's just kind of a helpful thing to think about if you're having trouble, getting your mind around what a function where you're graphing values in a fourth dimension would look like. You can think about color or temperature or something like that. And so another way we can actually start to visualize a function is look at what's called level surfaces. And just like level curves with a function of two variables mapped out curves in the plane for which the function had constant values, that's exactly what level surfaces are going to do. I can pick, say, a number k1 and set my function equal to that value. And what that's going to do is it's actually going to give me a surface in space where all of these x, y, z points on the surface have the same function value. So you can think about all the points on the Earth that have the same temperature. That's going to be a surface. And that surface will be a level surface for that temperature function. And just like with curves, we can keep going. I can find a different number and find the level surface corresponding to that. So maybe that's some sort of region inside that. And even these level surfaces are very hard to visualize, but again, fall back on the examples of temperature or color if you want, and just think about, like, if I look at a wall, it's the color blue. Well, I can think about the function given by the color of points in my room, and the surface that's that wall are going to be all the points in the room that are that color blue. So it's helpful to have these kind of, they seem silly, but they're really going to help us visualize what these functions of more than one variable are going to look like. And when you talk about electric fields or magnetic fields kind of existing in two-dimensional, three-dimensional space inherently, you can't see them, but you got to think like temperature or color. They sort of exist in a dimension beyond what you can see. Okay, so we want to find the domain of this function. And now notice that this is a function of two variables, first of all. So its domain is going to be a subset of the xy plane. And now we want to use the same basic rules that we had for functions of one variable. And notice here we have a square root. And so what do we know about square roots? Well, it doesn't make sense to take the square root of a negative number. So what we're going to do is require that what's underneath the square root, 1 minus x squared minus y squared, be greater than or equal to 0, like that. Okay, and now let's just solve or rearrange this equation. So if I add x squared and y squared to the other side, I get that 1 is greater than or equal to x squared plus y squared. So my domain is the set of points x, y, such that x squared plus y squared is less than or equal to 1. But this is points that exist inside the unit circle, because x squared plus y squared equaling 1 actually is the unit circle. So here's x squared plus y squared equals 1. If I want x squared plus y squared to be less than or equal to 1, my domain consists of points inside this circular disk here. So the algebraic manipulation here to find the domain is very similar to what you do in one variable. You just have to realize that the restriction on your xy points are coming from the plane, like regions like a disk or something like that. Alright, so here we have another function of two variables, and we want to find the domain and sketch it. So first we'll notice that we're taking the natural log of something, so we cannot take the natural log of a negative number or a number that's equal to 0. So what's inside the argument of this natural log needs to be strictly greater than 0. So that means x squared minus y needs to be strictly greater than 0. So if I add y over, then I have y is less than x squared. Okay, but that means I want the set of points x, y where the y-coordinate is less than x squared. Well, the boundary of this region is actually the parabola y equals x squared. But now it's strictly less than, so that means I'm not going to include the boundary. So if I sketch what this looks like, here I have this parabola. This is y equals x squared. And so the points I'm interested in the domain of my function are the points where the y-coordinate is less than this parabola. So all the points in this region below the parabola y equals x squared and not including the parabola because it's strictly less than here. Alright, so again we have a function of two variables, so its domain is going to be some subset of the plane. But here we just want to sketch the level curves, and so recall those are xy points for which the output of the function is some fixed value. So there's actually three values that we want to consider: 0, pi over 4, and pi over 2. So let's draw the xy plane and actually sketch these level curves. And so if we set k to be 0, what we want to do is we want to actually set this function equal to 0. So we have 0 is equal to arc sine x plus y. And now I just want the collection of points, x and y, for which this equation is true, and that's going to give me a curve and the plane, and that's going to be the level curve for k equals 0 for this function. So notice that I can take the sine of both sides. Arc sine is the inverse of sine. So I have sine of 0 is equal to x plus y, but sine of 0 is 0. So I have 0 is equal to x plus y. But if I solve for y, this is y is equal to negative x. But this is a line passing through the origin of slope negative 1. So my level curve is going to be this line, y equals negative x. So this corresponds to k equals 0. So this is like, if you want to think in terms of elevation, all of the points on this line has to have the same elevation. Now if I go to say k equals pi over 4, then again I just want to set pi over 4 equal to my function. And again, I can just take the sine of both sides. So sine of pi over 4 is square root of 2 over 2. Or in other words, y is equal to minus x plus root 2 over 2. But this is a line of slope negative 1 passing through the point root 2 over 2. It's parallel, my drawing doesn't really look like that, but it should be parallel to this line. So this corresponds to k being pi over 4, or outputs of my function that all give me pi over 4. And I can do something similar with pi over 2. So if k is pi over 2, I have pi over 2 equals arc sine of x plus y, or sine pi over 2 equals x plus y, but sine of pi over 2 is 1. So if I solve, I get y is equal to negative x plus 1. And now 1 will be up here, So I get another line corresponding to k equals pi over 2. And so I'm getting these level curves, and so what I see is that this direction is taking me uphill. So here, this is like an elevation of 0, an elevation of root 2, or pi over 4, elevation of pi over 2, etc. as I go this way. And these are all lines because actually this function will actually just give me these level curves. They're all lines like this because I can just, for any fixed value here, I just have x plus y is equal to sine of that fixed value, and so I'm just getting all of these lines of slope -1. Alright, so again, we just have these three values, 0, 1, and 2, that we want to find the level curves of this function. It's just x times y, and it's a function of two variables. So first notice that k is 0, then we have 0 is equal to x times y. But if x times y equals 0, then either x is 0 or y is 0. But this is just the y-axis, and this is just the x-axis. So actually the level curve here are just the two coordinate axes. So if I draw my coordinate axes, it's going to be a little weird. I'm actually just going to trace the two coordinate axes. And that's going to give me my level curve for k equaling 0. Okay, now let's say k is equal to 1. Well, then I have 1 is equal to x times y. And if I solve for y as a function of x, I have 1 over x. This is just the hyperbola 1 over x. So it looks something like this. There's another branch down here. That. This is going to correspond to k equaling 1. So now, again, in the back of our mind, we want to think about like a elevation map or something like that, where we have actually these level curves or these lines that kind of are giving us points of constant elevation. In that way, we can sort of see as we move across the level lines that we're moving either uphill or downhill. And so that'll become even clearer when we do k equals 2. So I guess first notice that for k equals 1, this is passing through the point -1, -1. This is passing through the point 1, 1. So when k is 2, what we have is 2 is equal to x times y, or y is equal to 2 over x. Now notice here, if I plug in 1 for x, y is going to be 2. So this is actually going to pass through the point 1, 2. So it's going to be outside, or it's going to be kind of stretched out beyond this hyperbola here. So there's y equals 2 over x, like that. So this is the level curve corresponding to k equals 2. And you can see that these are sort of tracing out inclines going up this way and going up this way, and then along the axes is sort of like sea level, so k equals 0, elevation of 0, like that. Of course, if you had negative values of k, that would sort of be like going beneath the ground. in some sense. And if we had negative values of k, they would actually go up here and down here. And so you can see this is like going uphill, up a mountain, this way and this way, and then we'd be going into a valley, this way and this way. So again, it's just going to be helpful if you can go ahead and start visualizing what the surface looks like for this given function. So we're going to do the same thing here. Let's draw our coordinate axis. Okay, and so what we want to do is sketch some level curves for k equals 0, 1, and 4. So if k equals 0, then we have the equation 0 equals x squared plus y squared. But this is extremely restrictive because x squared plus y squared is greater than or equal to 0. But here it's also equaling, it's just equaling 0. So actually there's only one point in the entire plane for which x squared plus y squared equals 0, and that's when x equals 0 and y equals 0. Or in other words, the level curve here is not really a curve, it's actually just the point 0, 0. So here's k equals 0, right there. Okay, so what about, say, k equals 1? Well, we have 1 is equal to x squared plus y squared. But this is just the unit circle. Oops, negative 1, 1, 1, negative 1. So we just have the unit circle. Those are going to be all the points for which the function outputs 1. So this is k equals 1. And then for 4, we'll have 4 is equal to x squared plus y squared, but this is just a circle of radius 2. So this will be our level curve corresponding to k equals 4. So this is going to be the set of all points for which the function outputs 4. And now, again, I'm going to try to attempt to help you really visualize what this function looks like, and I'm actually going to try to draw the three-dimensional shape. So notice that here we're starting at k equals 0, and as we expand out radially, we're increasing. So the elevation is increasing. So this is really like the bottom of a valley. So if we really looked at the three-dimensional graph of this surface, then what we have is almost like a bowl-like shape, like this. And these level curves are going out like this. So again, maybe this is, my drawing skills are not superb, but you can see that here's the middle of the bowl, and we're kind of going out like this. And these are just tracing out those curves where the bowl has a constant height going around in circles, like that. All right, so here we want to describe the level surfaces of this function of 3 variables here. And so this is already going to be significantly more challenging because we're not going to be able to necessarily visualize the actual function because it's going to sort of be sitting in 4-dimensional space. But we can start to visualize the level surfaces, or in other words, this collection of points that are giving me a constant function value here. And so one thing to notice here is that if we were to say, look at 1, so let's set the function equal to 1. This is z over 3 squared, like that. Well, maybe you're not exactly familiar what this looks like, but what we can do is look at the cross sections of this surface. So if z is 0, then we have circles of radius 1 in the xy plane. If x is 0, then we have 1 is equal to, let's see, y squared plus z over 3 squared. So this was a circle, radius 1. This is actually an ellipse. And then if y is 0, we also get an ellipse. So this is like in the yz plane. This is going to be the cross section of the let's see, x squared. This is going to be the xz plane. And see, it's also going to be an ellipse. So we're imagining a shape where, sort of going in one dimension, we have a circle. Another dimension, in the other two dimensions, we have ellipse. So what that looks like carefully. Here's the x-axis, y-axis, z-axis. So what we have is something like, in the z direction, we're going up all the way to 3, because think about like the yz plane. We have this ellipse. Okay. And then, so in the xy plane, we actually have a circle. And then in the xz plane, we also had an ellipse, like this. So, of course, there's different ways to do this. And, we're assuming, of course, if we have some sort of graphing software, we could graph this function, but kind of assuming that we don't have that. And so what we're seeing here is in one dimension, we have circles like this. And in the other two, we have these sort of ellipse shapes. And so you can see the region is this kind of ellipsoid, and that's actually technically what it's called, an ellipsoid. It's sort of like a stretched out sphere. And now in the x and the y, it just has a sort of a radius 1. In the z, it's stretched all the way out to plus or minus 3. So it's just kind of a stretched sphere like that. And now this was for k equaling 1. But you can see that if, for instance, k were 2 or 3 or 4 or whatever, that's just going to cause these surfaces to expand out, but they're going to have the same basic shape. The level surfaces are going to all be these ellipsoid. So that's ellipsoid, like that. All right, so again, we want to try to visualize the level surfaces of this function. And so you could pick anything you wanted, but let's say we picked k equaling 0, or in other words, the set of all points x, y, z for which the output of the function is 0. So we would have 0 is equal to z squared minus x squared minus y squared. Well, I'm going to rewrite that as z squared equals x squared plus y squared. And so this surface will actually be recognizable to you when we look at what it is. So for different values of z here, we're just getting a circle of radius c, because we have x squared plus y squared will be equal to the radius squared, which is just c. So if we look along the z-axis, so here's x, y, and z. So for instance, when z is 0, now this is just the k equals 0 surface, we'll have 0, and then if we go up to 1, we'll have a circle of radius 1. That. And then if we go up further, we're just getting circles of larger and larger radii. Like that. Let's step back and actually draw what this is. So let's use a different color here. So let's say k equals 0. We have the z squared equals x squared plus y squared. And actually, so there are circles in the xy plane as z increases, and actually the circles have radius that's just equal to z. So these circles are increasing in radius as z increases, like that. And actually we also have the negative direction as well. For instance, if z is negative 1, then we also have a circle of radius 1. Or if z is negative 4, we also have a circle of radius 2. So they also go down like this. But this is just a cone. So the cone goes up like this, and down like that. And this is the level surface corresponding to k equaling 0. So the points on this cone, hopefully you can visualize it, okay, are giving me outputs that are 0. And so what happens, say, if k is equal to 1? Well, these cones are just going to translate, but the general shape of the level surface are these cones. Yes. All right, so here we have this function x plus z, and we're looking for the level surfaces. So let's just say k were 0. So in other words, we're looking at the surface 0 is equal to x plus z. Well, this is just a plane. And in fact, in the xz plane, this is just the function z equals negative x. So if we sketch coordinate system, there we go. Okay. Then here's x and z. So this is the positive x direction. This is the positive z direction. And so z equals negative x. Well, that's going to be a line that's going to pass in the xz plane like that. And actually, for any value of y, we're going to get precisely the same line. And so the collection of all of these lines is giving me a plane. That, of course, will extend off. And hopefully I'm not covering up the picture too much. Let's back up. So all of these lines are parallel to the line z equals minus x in the xz plane here. And so they all cross through the y-axis, like this, because there's no z-intercept here. Okay, and then I'm going to extend out, so it's a slanted plane. It's this level surface k equals 0. And now if I say change to a different value of k, well, the plane would be translated, but the level surface would be the same. It would still be a plane of this form. All right, so we want to find an equation of the level surface passing through this point of this function here. And so how are we going to find the equation of the level surface when we don't have the actual output value? Well, that's where we're just going to actually find it. So the output value we're interested in is f of 1, negative 1, 0. And so let's plug in 1, negative 1, and 0. So we're going to get 1 minus 0 plus negative 1, that's 0, over 2 plus 0 minus negative 1, so 3. So that's going to be 0. So what we're looking for is the level surface corresponding to x minus c plus y over 2x plus c minus y equaling 0. Okay, so what is this surface? Well, the numerator is going to be 0 as long as the denominator is not 0. So, in other words, we have a fraction equaling 0. The only way a fraction is equal to 0 is if the numerator is 0 and the denominator is not 0. So we have the surface given by x minus z plus y equals 0 and 2x plus z minus y is not 0. So what does this actually look like? Well, this surface is a plane, but we're requiring that 2x plus c minus y can't be 0. So we're removing this plane. So if we take a plane and remove another plane, then from this plane, we're actually just going to remove the line of intersection between these two planes. So that's what it's going to look like. It's going to look like a plane with a line taken out of it. And what is that line going to be? It's going to be exactly the line given by the intersection of these two planes. So here's this plane that we're removing. Here's this plane that we want. So we're removing this line of intersection from this plane, and that's the level surface.